So in 5.6, we're going to talk about how to take the derivative of the inverse trig functions, so like arcsine, arccosine, arctangent, etc. And so before I just tell you what the rules are, we briefly talked about in class when we dealt with inverse functions how we could take the derivative of arcsine by taking advantage of the fact that I know what its inverse is, just regular sine of x, and I know how to take the derivative of sine, and that there's a relationship between the derivatives of inverse functions. And so I want to walk through that again in this video, but I want to simplify the derivative that we found in class so that it matches the rule that I'm going to tell you. At the end of the day, you just need to memorize the actual rule itself and not go through this proof, if you will, every time you need the derivative of any of the 6 inverse trig functions. So in this case here, if I want the derivative of arcsine of x, so I want y prime here, well, I could take advantage of the fact that I know the derivative of sine, and so I can essentially just sine both sides of this equation, and so I get sine of y equals sine of arcsine of x. And what's nice now is on the left side we get sine of y, and on the right side, since I'm composing sine with arcsine, they cancel each other out, and I'm left with x. Keep in mind right now, I have an implicit equation right here. This is implicit because y is not all by itself, but the y variable still represents arcsine, so I still want y prime. But at this stage here, I can take the derivative implicitly and get y prime, get the derivative of arcsine like I want. So let's go ahead and do that. I'm going to take the derivative of both sides with respect to x. So I'm going to ddx both sides. On the left, I'm taking the derivative of sine of y with respect to x, so I need to do it implicitly. I'll take the derivative normally, which is just cosine of y, and then since the variables are different, I need to multiply by y prime. On the right-hand side, the derivative of x is just 1. And from here, I can now solve for y prime by just dividing the cosine of y to the other side. And when we did this in class, we stopped right there and said that is the derivative. And I wanted you to see the pattern, that it was a reciprocal. You have a 1 over. In the denominator, you see the derivative of sine, which was the inverse function, just a cosine. And there was a y in there rather than an x. Today, I want to emphasize how the rule in your book matches that rule right there. And the key, first of all, is, okay, typically if I have y equals arcsine of x, the derivative I also want to be in terms of x. So how can I get rid of the y? Well, again, I know that y equals arcsine of x. So I'll start there. 1 over cosine of arcsine, of x. That's an arcsine of x. And at least right there, that is a derivative in terms of x. But unfortunately, that is also not the form of the derivative, although equivalent. It's not the form that you would see in the book. So where is that coming from? And up here in blue, this is just a little reminder. You did this in pre-calculus, in that you composed last year a trig function, in this case cosine, with a different inverse trig function, arcsine of x. And I just want to refresh ourselves how we do that. Although remembering this skill is not essential to the course, it is something you did last year, and I just want to walk through it so that we can emphasize why your pre-cal teacher taught it to you last year, and just to prove where the actual rule from our book comes from. All right, so how do we simplify cosine of arcsine of x? Well, this piece right here, this is representing an angle. This is an angle whose sine value is x, or simply put, whose opposite over hypotenuse ratio is x over 1. And so what you did last year was you created a triangle, and you said, okay, there's the mystery angle theta within my right triangle, and I want to create a triangle so that the sine value is x. So the opposite side is x, the hypotenuse is 1. Okay, so again, sine of theta right now on my top right blue triangle is x over 1, opposite over hypotenuse, which is x. I now look and I want to take cosine of it. I want to look at the ratio of this triangle because this right here is now theta. Okay, so think of that as theta. I'm basically asking you, what's cosine of theta? What is cosine of theta for that triangle I have drawn up there? Well, cosine is adjacent over hypotenuse. What's the adjacent side? Well, I don't know it, but it is a right triangle. I know two of the sides. And so if I do Pythagorean theorem, a squared plus b squared equals c squared, I'll just call this a for now. A squared plus b squared equals c squared, or 1 squared is just 1. I can now solve for a. I could solve for a by subtracting the x squared to the other side and then square rooting it. We do have a plus or minus case, but here, since it's representing a length, we'll keep it as the positive root. And so a is the square root of 1 minus x squared. And so I'll put that in my triangle up here. And now I'm able to do adjacent over hypotenuse. And so I'll write it here. So 1 over, what's cosine of that angle? It's going to be the square root of 1 minus x squared over 1, or simply put, the square root of 1 minus x squared. And it's this rule right here that you're going to see in your books for the derivative of arcsine of x. That, again, is what you should have memorized. But I wanted to walk through here in that you could derive the derivative rule through taking advantage of inverses and implicit differentiation, which we did on the left side of the screen, and then you just need to simplify it to make it match. But enough of the proof. Let's walk through and list all of the derivative rules. Okay, so arcsine of x, we just established, is going to be 1 over the square root of 1 minus x squared. Arcsine of u, I'm not going to list all of these rules with both chain rule and without chain rule, but I will do it for just arcsine, and hopefully by this point you can apply chain rule on your own, or if you want to put the chain rule in your notes, you can do so at this time. So arcsine of u, well, I just need the chain rule, so it's going to be 1 over the square root of 1 minus u squared, the derivative rule normally, and then chain rule says I have to then just tack on or multiply by u's derivative. All right, so let's go through the other ones. Arc cosine of x, it's going to be the same rule as above, just negative. So arc cosine of x is going to be negative 1 over the square root of 1 minus x squared. Again, I'm not going to write it out explicitly, but if we wanted the chain rule, if it was arc cosine of u, it would just be negative 1 over the square root of 1 minus u squared times u prime. What you're going to see as we go through these rules is that they are going to be paired into groups of 2, where one will be the rule positive and one will be the rule negative. So here, arcsine of x is the positive, 1 over square root of 1 minus x squared. Arc cosine is the same thing, but just negative. Arctangent. So for arctangent, its rule is going to look like this. It's going to be 1 over 1 plus x squared. No square root. Just 1 over 1 plus x squared. For arctangent, it'll be the same thing, but just negative. Negative 1 over 1 plus x squared. Arcsecant and cosecant, again, are going to be paired up. Arcsecant is going to be 1 over the absolute value of x times the square root of x squared minus 1. And arc cosecant will be the same thing, but just negative. So negative 1 over the absolute value of x times the square root of x squared minus 1. So those are the 6 derivatives for any of the inverse trig functions. Please note that I listed again all of the derivative rules for the parent functions. If there's anything other than just plain old x on the inside, we would need to apply the chain rule like we've been doing all year. So let's look at a few examples together. All right, so find y prime. Okay, so all of these are going to at least use the chain rule. So I'll do it here in blue. So for the first one, if I want y prime of 3 arcsine of x cubed, it'll be 3 times the derivative rule for arcsine. And arcsine says 1 over the square root of 1 minus, and we had 1 minus x squared. How you're going to hear me say it is it's going to be the square root of 1 minus the inside squared. So it'll be the quantity x cubed squared times the derivative of u, which again, u is going to be the inside. That's my u. So it'll be times 3x squared. So in any of those rules, when you see x, you're going to hear me say the inside. Okay, so again, the rule, the derivative will be 3 times 1 over the square root of 1 minus the inside squared times the derivative of the inside. Let's do it again with arctangent. With arctangent here, we will need the product rule because we have a 4x times an arctangent. So the derivative of 4x is 4. We leave the arctangent as is, plus, leave the 4x the same, and now the derivative of arctangent. And I'll switch to red just to emphasize this is the derivative of arctangent, our new rule for today. Arctangent rule said 1 over 1 plus x squared. So it'll be 1 over 1 plus the inside squared times the derivative of the inside. The inside was e to the 2x. How do I take the derivative of that I have circled in red? That will be itself times 2, because it would also need the chain rule because it has something other than just plain old x in its exponent. But those are some examples of how we would use the derivative rules for arcsine and arctangent. All right, let's just do one with arcsecant just to practice its rule. So for arcsecant, the derivative, if you were to look in your notes, it's 1 over the absolute value of x, and x is representing the inside. So 1 over the absolute value of the inside times the square root of the inside squared minus 1 times the derivative of the inside. The derivative of x over 2 is just 1/2. All right, so let's end with one application, and I like this example just to further practice how to evaluate our inverse trig functions. So find the equation of a tangent line. Okay, so for a tangent line, we need a point and we need a slope. I give you the x-coordinate, so we get the y-coordinate by just plugging that on in. What's f of negative 1/2? Well, that's going to be our cosine of negative 1/2. And so remember, when we evaluate an inverse trig function, the question you're always going to ask yourself is what angle in cosine's restricted domain gives you a value of negative 1/2. And so for arc cosine, cosine's restricted domain was between 0 and pi. So that's the first and the second quadrants. So in the first and second quadrants only, where does cosine have a value of negative 1/2? And that's going to be in the second quadrant at 2 pi over 3. So the y-coordinate will be 2 pi over 3. And now I need the slope, because again, in the equation of a line, we need a point and we need a slope. We always get the slope of a tangent line through the derivative. So let's get the derivative and then plug in negative 1/2. The derivative rule for arc cosine of just x, this is the parent function, so we do not need the chain rule, is just going to be the negative 1 over the square root of 1 minus x squared. Oops, so I'm not going to set that equal. Underneath it, we'll use good notation. F prime of negative 1/2 is going to be negative 1 over the square root of 1 minus negative 1/2 quantity squared. If you decide to further simplify that derivative value, feel free. But for time's sake, I'm just going to use that value as is and present my final answer. What is the equation of the line? I'll use point slope form as always. Y minus 2 pi over 3 equals my slope, which I'll wrap in parentheses, that negative 1 over the square root of 1 minus negative 1/2 squared times x minus negative 1/2. So the double negatives, I'll just put it as positive. But that would be the equation of my tangent line.